We trust our GPS with just about everything, right? It gets us to that new restaurant, it guides us on a hike. We just assume it works. But what happens when that trust is broken in a situation where you absolutely can't afford a mistake? Well, today we're going to dive into the high-stakes world of aviation, where a single cryptic warning can mean the difference between a perfect landing and a real emergency. Okay, so picture this. You're a pilot, you're on final approach, the weather is awful, you can barely see a thing, and you are relying completely on your instruments. Then, this message flashes on your screen. Now notice, it doesn't say GPS signal lost. Nope, it's saying something much more subtle and a whole lot more dangerous.
So, what on earth does that actually mean? It's a message that the very system designed to guarantee your safety has, well, it's lost confidence in itself. And that's the big question we're going to unpack right now.
To really get what that warning is all about, we first have to meet the guardian of your GPS signal. It's this amazing system working behind the scenes, and its name is RAIM.
RAIM. It stands for Receiver Autonomous Integrity Monitoring. Now, the big word here is autonomous. This thing is a self-contained integrity check living right inside your GPS receiver. Honestly, the best way to think of it is as a built-in lie detector. It's constantly asking one simple question. Are all these satellite signals telling me the same consistent story?
And here's a great way to picture how it works. Imagine each satellite is a member of a committee, and they're all voting on your exact, precise location. RAIM is basically the chairperson of that meeting, listening to all the votes to see if everyone agrees, or if one of those members is saying something totally out of whack. But for that committee meeting to even be official, you need a quorum, and in the world of RAIM, that magic number is 5. As long as the receiver can see at least 5 satellites, the system has enough votes to cross-check everybody and spot a potential liar in the group. So it all boils down to this really clever 3-step process. First, step 1, RAIM makes sure it has its quorum. Yep, at least 5 satellites. Then, for step 2, it starts comparing different combinations of those satellite signals. It's asking, okay, if I use this group of 4, where does it say I am? How about this group? And finally, step 3, if one of those combinations gives a position that's way off from the others, it flags an inconsistency and bam, the alarm goes off. So when RAIM does detect a problem, what happens? Well, it doesn't send a polite email. It issues a digital stop sign that a pilot absolutely cannot ignore. And this part is so important to understand. A RAIM failure doesn't mean your GPS has just died. You might still see your little airplane icon moving on the map. What it actually means is a complete loss of trust. The system is screaming at you, hey, I'm still getting signals, but I can no longer promise you they're accurate. And this happens for one of 2 reasons. Either you dropped below 5 satellites or the cross-check just failed. To really get the seriousness of this, you have to know that in aviation, an instrument flag is like the ultimate red alert. It means the data from that tool is garbage. And this quote here puts the RAIM alert on that exact same level. It's not a suggestion, it is an order. Stop using this instrument right now. And that order kicks off a protocol that is totally non-negotiable. If a pilot sees that warning during an instrument approach, they have to abort immediately. They switch over to their backup navigation, maybe some old-school ground-based radio beacons, and they get on the horn to air traffic control to let them know their primary GPS is no longer reliable. Okay, but now, this is where it gets even more fascinating. See, not all errors are created equal. Some are really loud and obvious, but others are dangerously quiet. And this brings us to a cool concept we can call an error's sneakiness score. All right, so the super technical term for this is the failure mode slope. All it is a ratio. It compares the size of the actual error, how far off you really are, to the size of the tiny inconsistency that RAIM is able to detect in all that satellite data. Let's break that down. Think of it like this. On one side, you've got the real danger. Your plane is drifting way off course. But on the other side, you've got the only clue RAIM can see, a teeny tiny, almost invisible inconsistency in the signals. The ratio between how big that danger is and how small that clue is, that's what we're talking about. So to make this way more intuitive, we're just going to call it the sneakiness score. A low score is great. It means you get a big clue for a big error, so it's easy to spot. But a high score means you're only getting a tiny little clue for a very big and very real problem. That is one sneaky fault. And this is where it gets a little bit scary. A high sneakiness score is dangerous because the real-world error could become hazardous long before the clue is big enough for RAIM to even notice. And an infinite score, that's the absolute worst-case scenario. It means the error is a perfect ghost, totally invisible to the system. It's messing with your position, but it's not leaving behind any tracks for RAIM to find.
All of this leads us to this really stunning paradox in modern navigation. You'd think that as we launch more and more satellites, our systems would just get safer and safer. But the reality is a lot more complicated.
I mean, it seems logical, doesn't it? More data points, more members in our global satellite committee meeting should make it way easier to spot the one that's lying. And while that's totally true for simple, single errors, it also kind of opens the door for brand new, much more sophisticated problems. Just look at this comparison. On the left, if you have a whole bunch of satellites and only one of them is bad, that error sticks out like a sore thumb. The sneakiness score goes way down, which is great. But look at the right. If you have multiple satellites all sending out a coordinated faulty signal, like in a sophisticated spoofing attack, it actually becomes harder to detect. Those bad signals can create a new, false consensus that looks perfectly normal, and that makes the sneakiness score just skyrocket. This table right here just summarizes the whole paradox perfectly. That first row shows that if you're only dealing with one fault, adding more satellites is a good thing. The sneakiness score goes down. Awesome. But the second row shows that if you have a fixed number of satellites, adding more faults is a bad thing. The score goes up. And that last row? That's the mathematical recipe for creating a perfect undetectable ghost error. So the big takeaway here is that just throwing more satellites into orbit isn't some magic fix for navigation safety. Sure, it solves some problems, but it also creates brand new vulnerabilities, giving these complex coordinated errors new ways to hide in plain sight. And that really leaves us with this final crucial question. In an age of massive satellite constellations and new threats like spoofing, our navigation systems are getting unbelievably complex. So how do we make sure our guardians, systems like RAIM, can evolve fast enough to keep up with the ever more clever ghosts that are hiding in the data?